Welcome everyone to the next session of Carla simulation and of self-driving car simulations in general. So in the previous two sessions, we had short introduction about Carla simulator and how we can use it to develop or to implement a very simple longitudinal and lateral control. Starting from now, from this session, what we will learn is basically how we can implement or actually use different sensors of Carla first. And these sensors are like lidar sensor, radar, and also different camera, I would say color space, and mainly the semantic segmentation feature of Carla, which we see it here, for example. And what we will learn also is how we can use this sensor data to do lane detection like we see here, and also how, for example, to estimate the path like we see there. For example, what is important here is for example, the target point, which is there. And for example, later is how we can use this target point using the detected lanes, using the detected path, and the depth camera information to estimate the real, first of all, or the 3D position or the world position coordinate of this point, and then use that as a target point for our control systems like pure pursuit controller or Stanley controller, for example. So as I explained at the beginning, so self-driving cars has a perception part, and today we're talking about the perception, and it has a controller part. Controller, we talked about controllers, two examples of controllers. Of course, there are other controller types like the model predictive, for example, controllers, and the neural network or deep learning based or reinforcement learning based controllers. Um, so these controllers, they need reference, as I said, and what we are doing today is to use the perception part or to develop the perception part because we want to get the reference, we want to get the target point, and then you need to use this target point to develop or basically to use it for the controller. Now, of course, uh, what modern self-driving cars and mainly Tesla do, or with what we think it does, is basically that they are more focusing on full or end-to-end basically learning, what is called in deep learning, which means all the steps that we are doing now probably they don't do, like semantic segmentation, lane detection, and search for reference points, or they say that they don't do them. I don't know. Uh, but basically what they claim is that they use only image, just the image of the scene. But so in Tesla they use three different cameras, or actually multiple cameras as inputs, and they use and of course the output would be of the neural network, the steering angles, the throttle, and the braking, and so on. Now, from basically what I recommend is, especially we don't have the data, or if you are starting your self-driving car research, you won't have the data that Tesla has, because of course, if you have data Tesla has, basically you can probably have the end-to-end model that is doing everything because it's a huge data set. If you don't, you need to have a combination between as I said, like symbolic systems, like traditional control systems, and you need to use pre-trained models to, for example, to do the semantic segmentation, and then to use or to do like classical machine vision, tasks or techniques for lane detection, and then, for example, you would do like polynomial fitting, as we'll see today, to estimate the path and so on. So basically, what we will learn in this course is how we can combine different systems to achieve self-driving car, or mainly level 1 self-driving car. Now, in addition to that, if you want to go to level 2 or more, we need to use other machine vision systems. like object detections, or for example pedestrian and vehicles detection in the scene, because in this case we need to adopt, for example, our it's getting heavy, so let's stop this. We need to adopt basically our so the controller use the lateral and moment yeah, the controller use the lateral and the longitudinal basically references, right? So we have longitudinal reference and we have lateral reference. Now the longitudinal reference would change, for example, the speed in this case, or the speed, the plan of the speed would change if we see a vehicle in front of us, because we need to slow down. So we need basically to reduce the speed, and we need to give this reference for the controller to slow down basically, and then the controller would of course control the throttle and the brakes to achieve that new reference. And also, yeah, the lateral basically might change if based on object. Of course, if I want to let's say change my path, if I want to do lane departure, to change my lane, for example, to overtake a vehicle, then that also we need to do path planning, then we need to follow that path. So these are affected by, of course, the object detection, because we need to detect different objects, like detecting also traffic lights, and when I see traffic light, then I need to slow down, which means I need to give new reference again for the longitudinal control. So if you see basically what I am saying is that all then would depend on, or actually all our inputs to the longitudinal and lateral control, because they control of course how the vehicle works, either turn left or right, or basically brake or speed up. And the inputs to this controller are the references. These references are subject or functions of what we have in this scene. Like the lane detection is one, because lane detection is used for path planning, but not only lane detection, or lane detection basically is used. You would have different for example references for the lanes, or basically for the path. The vision based, which is could be lane detection, one part, and the other one, as I said before, could be GPS information, could be a pre-planned path for vehicles. Like as I said, Tesla, they drive mainly in, for example, in California and US in general, but for example, California, and so most of the cities that Tesla is really active in, or actually is very popular in, I'm pretty sure that it's already have built in the city map itself, and also the path that it would take, for example, different recall location of that city, because it can use this path for the path planning. As you know, it would know where are the traffic lights, it would know everything, and I'm pretty sure that basically that information is within self-driving cars. So but in our case here, we would rely only on vision. You can actually use this information from Carla simulator, because it is a simulator, so you can know where the traffic lights are. And what we will see actually now, or you have seen now running, is the autonomous, or the autonomous control part of Carla. So you can just turn on the autonomous basically part, and what so you have seen is basically the car driving itself. But that is not really autonomous. It's also more like the car knows the map, or the model knows the map and knows where are the traffic lights, when it needs to stop, and so on. It has some intelligence, but basically it's more like built in. Okay, so the first task we would start with is the lens detection. Now, lens detection is, and basically what we are using, or what we are relying on here, is machine vision. And of course, deep learning, machine learning is part of machine vision, but machine vision is more than machine learning and deep learning. But I will upload to Moodle basically this, let's say, code, which has some placeholders where we need to add our basically new code. Now, this code is not that different from the other Carla examples that we have seen in the example folder. The main difference is here that basically in this code, first of all, I will go through all the classes inside or the object. First, it has predefined sensors that we can use. It has the normal camera, which is the RGB camera. It has different depth cameras that we can use. We have raw and depths, and here basically the logarithmic depth. And we have the semantic segmentation, so the raw semantic segmentation, and the cityscapes basically palette semantic segmentation, which is it is semantic segmentation that's trained on basically this data set that I will show you later. So semantic segmentation is not the camera. Semantic segmentation is you have a camera, although it's written as a sensor in Carla, but actually it's not a sensor. It is a camera, and after this camera you have deep learning model that's doing the semantic segmentation. Now, when you look at the semantic segmentation in Carla, you see it is perfect. So there are two options here. One is that you use the perfect semantic segmentation, which actually not the prediction. It's also built in because you would see like perfect segmentation, and in reality, because it's deep learning model, it's machine learning model, you won't get that perfect segmentation. It's close to perfect, but not that perfect. Anyway, so we will use here basically the perfect segmentation because we are caring more about what after that, what after the segmentation, or what after the sensor itself. Now, this is the first part that I want to highlight. The second basically that here, in the previous example, I showed you how to use Pygame, and the Pygame is basically receiving the scene from the server, which is this one, the Unreal server, and then it's rendering it in Pygame basically, or Pygame environment. Now here we are not relying on Pygame, we are relying on OpenCV. And OpenCV, I don't know if you are familiar with, there are some machine vision courses within Carla University, and OpenCV is one of the tools or packages that you can use. Yeah, it is a machine vision basically tool or package that support 3 languages, C++, Java, and Python. It's basically very common, very famous, and I think it's been yeah, it's been used like for the last more than 10 years. And it has been, of course, it's always developing, and I think it belongs to Microsoft. I forgot, but yeah, I think it belongs to Microsoft. Anyway, OpenCV has many tools or functions or methods that you can use for machine vision, and this we will also use it to render images. So you can use it to render scenes. That's what we have seen before. This for example Windows, they are OpenCV windows. Yeah, so it's basically the second difference here. Now, before going into the code, because as I said, I talked about semantic segmentation as one now important component we would consider in this course. So what is semantic segmentation? The idea is basically that we have scene. Just looking at a better image for you. Yeah, so we have basically so we have a scene. This scene received by camera. We would like to do first segmentation. What is segmentation in machine vision? Is basically first the localization of pixels or pixels within the image, and then, for example, classify these pixels into a category or class. This basically the detection part. So basically you detect an object, you classify it into a person, car, street, whatever. Then the segmentation is basically the localization and, for example, the boundary detection of that object. So what we look here is that, for example, what is a semantic segmentation? Semantic segmentation is the same, but actually it doesn't, because we have detection and we have segmentation, semantic segmentation. Detection usually is about separate objects and localization of this object in the scene. Semantic segmentation, it goes basically a bit lower, I would say, level, because it's looked at the pixels, and these pixels, they belong to, of course, an object, and it will color or actually classify these pixels into different categories. So detection in general is basically you would see a region. It would classify a region within the image into different objects or classes. Segmentation, it will basically goes more into a lower level, so it will go into the pixel level and then classify these pixels to different object or classes. This basically what we see here. It's semantic segmentation usually have, of course, many classes, and when it comes to self-driving cars or basically autonomous vehicles, of course, as we see here, there are different classes that we are of interest. Like we have pedestrian is one class, we have street, for example, is another class, or road is another class, and we have for example, road markers, and lanes belongs to, or lane edges belongs to road markers. We have trees, vehicles, of course, buildings, and so on. I'll show you now the classes of that Carla considers. Anyway, so the idea is, if you are familiar with machine learning, then basically it is first classification. And by the way, we will go more into details in machine learning course if you are attending it in summer semester, because semantic segmentation is deep learning model, and we'll talk more about that in this basically in this class and in the machine learning class. But now I'm just basically using that model for self-driving car. Now, having said that, basically semantic segmentation is a deep learning model, as I said. I hope this, yeah. So what is the idea there? That first we receive an image, and as I said, we need to classify each pixel of that image to one of predefined classes, like cars or vehicles, roads, road markers, persons, and so on. Now, of course, this classification is not based on only the pixel itself. It's based on the pixel, the surrounding of that pixel, and the whole picture. This is why it's called semantic. So it's about the context where this pixel belongs. So it's not about the color only of the pixel itself, but the color of the pixel and everything around it. And maybe not only the color, of course. You could consider other features for that, for the detection, like depth, for example, pixels, and so on. So semantic segmentation usually is it's a neural network, it's a deep neural network, and it belongs to autoencoder family. So what is the idea of autoencoder family? Is that first, in autoencoder you don't have target class, or actually this is too much details about it, but the idea is that for autoencoder, the most important thing is that you have a feature space, like an image, and this will be used as an input to the neural network. Then what the neural network does there is try to compress that feature space into a lower space. Now this lower space is called the latent space, or the representation space. What the idea of representation space is, basically it is like, if you are familiar with PCA, it is much similar to PCA. And just give you a very simple example. If I'm trying to forget about semantic segmentation, if I have, for example, a million images of human faces, and I would like to use an autoencoder, like convolutional autoencoder like this, and convolution is one of the type of how the features will be processed within the network. And for example, what we want to do is that we would want to feed this network with this image of faces and repredict them again. So it means that you have, for example, the face of myself, then it will compress and try to predict the same image, exactly the same image. Now, what is the purpose of that, you would say, is that, why I would need to predict the same input if I have it? Well, the purpose is the representation here, because what I want to do after training this autoencoder with, let's say, a million of images, is that I would have here a representation space. And this representation space is a vector. And this vector, just for example, let's say it has 3 dimensions. Okay. What we would achieve, for example, at the end is that after this training is that dimension A is a dimension that represents, for example, the color of the face or a face, and dimension B represents the color of hair, and dimension C, I don't know, the face itself. Then if you manipulate, let's say now, if I split this network, now I take only the right part of it, and then I just feed this network with inputs in this 3-dimension space. Maybe if I increase the dimension A, the value of dimension A, then I'm moving the face color from, for example, dark to lighter. And if I, for example, move the or translate along the dimension B, then the hair would go from, I don't know, black to blonde and so on, and this would be generated. So the idea of this compressed then, or it's called also encoder decoder or encode decode, is that we need to build this representation space in general. And all deepfake, for example, or these new things that you see, they are based on 2 neural network models. One is called the generative adversarial networks, and the other one is basically autoencoders like this one. Now coming to the segmentation, it's the same, but here we have not the same image, we have, let's say, same image but with different colors or color maps. This is the idea that at the end we take the same image, we do the compression, then we try to predict the class of each pixel. So it's not like it is like classification task, but here we don't have one only target or one output where it would have different classes. We have number of classes equal to the number of number of outputs is equal number to number of pixels. Number of classes is equal to the number of our interest of classes, like we, as I said, cars, roads, and so on. Now, so it is a classification task. It's basically you take an input and you have different classes, and then you color this scene based on these different classes. Now there are different types of semantic segmentation. One of them actually doesn't do the decoder part. Just it goes like encoding and then try to predict a vector. Let's say if this is 1000 by 1000 image, then it will predict, it would have like 1 million output here directly, and then each output will represent a pixel in that image, and then it will predict, of course, the class of that pixel, and it will then rearrange it or reshape it to the image shape if you want to see it. And there are different types of semantic segmentation. SegNet is one of the basically state of the art, but also there is ResNet, which is also much better, especially for problems like for deep neural networks to avoid gradient vanishing and so on. If you don't know what I'm talking about, no worries, because for this course, as I said, what's important is what we get out of this network. Okay, so this is basically, if we check Carla semantic segmentation, which is, as I said, is considered as a sensor there, but is actually a step usually after the sensor. You would see here that you have an original image, then you have, this is the color conversion, but actually this is basically the semantic segmentation. You would see like cars in blue, for example. There are different colors actually if we now plot them or see them within the engine, but you would have one color for cars, one color for road, one color for trees, and so on. And these actually are the classes, standard classes. We have, for example, buildings, fences, other pedestrians, poles, and we have road lines, which is this is what we it is interesting for us for lane detections. We have also roads, and we have the sidewalks. We have, for example, trees or forests and so on, or vegetation, and we have vehicles, walls, traffic signs. Now, as I said, these they represent different actually colors, and we can get the colors. I'll show you inside the code. What is interesting for us is only the color, of course, of uh, this one, and currently what is interesting, and this one, or actually for us mainly this one now. And yeah, so basically later if we talk about detecting other objects, we can use, for example, the information about the pedestrians and about the buildings and so on to, as I said, use other inputs for the simulator. Okay, so this is one thing. Now moving back to our code. Now this code, as I said, is a standard Carla codes, but with a lot of additions. It has different classes or different objects. The first one is basically the keyboard control, and this is if you are using the manual control, not the automated or the autonomous control. Then here basically not only for manual control, this is basically the object that is handling or all the keyboard actions. And if I look here, I still have no name for this standard. Um, actually it's more like okay, so the first parts, this actually we don't need, is like what we have seen before. We are importing Carla, we are importing some standard packages that we might need like NumPy and so on, and we are importing CV2, which is an open CV. If you don't have it, after you activate your Carla basically environment, if you are using Anaconda, you need to basically install OpenCV2 for Python. So it's basically pip install OpenCV Python. And once you install it, basically you can then use it, and this is the where it's import CV2. Okay, so this basically, as I said, the class that is used to receive all the input actions. For example, if I press tab, which is key 9, it will change my camera. So it will actually switch between the sensors it will actually switch between the camera. There are two cameras, one inside the car and one outside the car. So one in basically like from the view of the driver, and one it's called third player, or actually yes, third player camera, which is like it's not the in car, it's outside of the car. And if I for example, if we start this, okay, let me start the other one. No, not leader. So we are now inside the car, and if I press basically tap, we get outside. That's basically just to switch between inside and outside, and we have here the Tesla Model 3 as a car. Okay, so we have here different keys, and it is documented with what is the role of each key actually, or keyboard. Key, none of them is that important for us except the manager or the camera, which actually what you'll see down is that when the game starts I already do that, which means because I want the standard view when the game starts or when the simulation started, that outside of the car, but I want inside the car because this is what is realistic first for the driving cars, and this is what we need for lane detection. Yeah, so this basically regarding the receiving of the inputs. You can also for example switch between autopilot and as you see here, between autopilot and manual pilot, or basically between the autonomous mode and the manual mode. And if you are basically with the manual mode, then you need to look at these keys, which are used for example for the control, like the steering control, braking, handbrake, and so on, which actually if you are now developing our controller, we need to look at this code because this is how we send the control inputs to the simulator. Okay, because with the autopilot we don't have any action, or we don't have any control. It's autopilot within the engine itself. So we need to consider that for the autonomous, for our autonomous mode. Now, before the HUD, actually, I'll come back to the HUD part. But here, let's talk about the main actually class, which is the world class. Now here they are different details, but I will basically come to details that we really need. The first thing is of course that we need a vehicle, and we need the HUD, and we need word. Now this is the Carla word, which is basically is what we have here. So we first, as you remember last session, we initialize this word. We can change the map for there are different maps, we can change them, and this basically then you will pass it to this object as you will see down. Then we have the HUD basically, and this basically the scene, or actually this is the OpenCV rendering mainly of the scene, and this basically where we can add all the detected lanes and all the annotation we want. Now we have blueprints, and here these blueprints are the this is basically the random blueprint, which is the random location of the actor within that scene, because we will spawn this vehicle in a random position, and you will see it here. So we are spawning that. There is a collision sensor, as you will see up. This collision sensor is when the car collides with either walls or other cars and so on, you will get a signal of collision, like a step signal, and you can use this signal, for example, for your machine learning model, or mainly for reinforcement learning models, like when the car hits something, you get negative reward, for example. We have here two sensors that we define. We have the raw camera, and we have the semantic camera. Now the camera manager itself, because it's the same object, it has basically it also takes input from your keyboard, and if they are basically your keyboard number like 1 to 6, if you move through them, you switch between one sensor to another sensor. Let me show you. So here we have basically the raw camera, and this is our main camera manager. If I press A, or I press 1, sorry. Then one is the row that we had, and 2 is also, it's basically one of the depth cameras. 3 is also depth. You remember we had 3 depths, and this is the logarithmic depth camera, and logarithmic, as you see, it's more like it's a bit more clear. 5 we are not getting anything, and 6 is basically our semantic segmentation, which is this one on the right. Okay, so this is basically the different sensors. So what I have done as a change to that standard code is instead of doing the switch, because anyway I needed semantic segmentation, actually I added this part, which is creating a new reference to the, or creating basically a new instance of that class. And this basically, here you can specify which sensor you want. So 0 is the raw. We have seen basically up the list of sensors. 5 is our camera, semantic camera sensor. Now there are other sensors that you can add to your simulation. For example, you can add, you have the leader, as I said, or LiDAR. You can use radar also, or radar as well, sensors. So there are different sensors, and you can sensor synchronization, for example, from Carla itself. And yeah, let me do that. So there's something you need to consider. I don't know if you have realized that or not yet when it comes to Carla. So we have the server, right, which is our game here. Now every script we run, it communicates with that server, right? So actually I can run in parallel 5 different scripts doing different things with that server, which is basically the environment. For example, I can run 5 different, or I can spawn 5 different autonomous cars, and then they will all run in this environment. And actually if you here in the environment, you can, of course, it's a bit slower in my case now because I'm using VM. Okay, anyway, so because it will take us some time, so what we need to consider, okay, let me for example activate another Carla environment because I need it. Yeah, it was called Carla V environment. Yeah, then yeah, we need to again, so we need to go there. Yeah, so now we have 2 windows that we can use to communicate with the server. And yeah, the first one is our OpenCV, or basically semantic segmentation lane detection. And for example, here I can run, I think it's called the sensors. What was the name? Oh, we have to go to the location tab. Sensor synchronization. Yeah. So here we're getting 4 one, two, three, four, basically in addition to the camera sensors. So these sensors basically are reading constantly the data from for this car basically, and you can of course get the data of these uh, four sensors. Like we have two radars and two lidars. Okay, that you can use, for example, as additional inputs for your model. If you are using, let's say, machine learning model, I'll try this open leader and see if it will actually communicate with the same. So here we see the leader, which is the 3D reconstruction. However, I don't think it is our car, because this actually is not moving. Yeah, the question why it's not moving. uh, no, it is not the same car. Anyway, but basically you can use the same logic to get leader information. But as Elon Musk said, leader is lame. So, but if you want to use it, use it. This basically, um, yeah, you can also, of course, when again we can spawn some cars like we have seen before. Okay. So there are 100 cars and 36 walker spawned here. So we should see some cars. So there are cars in the scene. You can see they added to the server. Yeah, as you can see them here as well. Okay, so anyway, this is basically what I wanted to say. You can actually communicate with the server using different scripts. You can add different self-driving cars. You can have shared server, and maybe you from your different laptops you can uh, communicate with the server. You can create competition between your cards and so on. So that all possible. Now this is what we add here the camera or the semantic. We can change weather in general. I will not consider this here, but you can actually change weather using the weather keys there up there. Now what is important is that when we start the game, and we will go to the other part of this code later, but basically um, What is important is that if we go down, we will see when the game starts. Okay, so it's basically the main part, where here we have the client, we get connection with the client, and then we create an instance of the HUD, and then basically we create an instance of the word, here taking the word from the client and sending the HUD that we have created. Then here I toggle the camera because I want to switch to the inside camera. And then here basically also for the semantic segmentation sensor, I also toggle the camera because also the semantic segmentation I want to use inside camera. Then here in case we are using the keyboard controller, or basically non the autonomous vehicle controller, then we use the keyboard controller. But here in our case we didn't toggle or activated the manual control, but the autonomous control, so the car is driving itself. Now what is important later here, now we have while true, which is basically the game loop, and at each step of this game loop we are actually rendering, so we are calling word.render. Now I'll stop now. In the next session we'll talk about what is word.render. Thank you.